Is that, yeah. Okay. Actually, okay, so yeah, do I like, all right. Okay, sorry about that. No, it's okay. Okay. Right, so we're going to run the notebook again from the top. You should run all the cells that you wrote yesterday, and if something wasn't working yesterday, you can copy my solution out of the notebook. It's all at the link that I dropped in the Slack. So hopefully you should be seeing a pretty fast download happening right now into your notebook. I'm going to go ahead and run all the rest of the cells that we did yesterday, and then you all should do the same. Everything down to the generating the HOD centrals part. So we did core func yesterday, blah, blah. And then while this is running for everybody, okay, so just a reminder, you should be running down to this section titled Generate HOD Centrals, because that's where we're starting today. And while this is running for me and everybody, I will recap what we did yesterday. Okay, so remember the idea is where we have a halo catalog from an n-body simulation. This is a dark matter only simulation, does not have galaxies in it. But we have this idea from the galaxy halo connection that galaxies live in dark matter halos. And so we want a model to paint on luminous galaxies to this dark simulation. And the model we're using is the halo occupation distribution, which assigns a certain number of galaxies to an individual halo based on that halo's mass. So yesterday we explored the catalog, we plotted the halo density field, we saw the cosmic web. And then we made a selection on the halos by mass. And just to sort of explore the properties of the clustering, we used core func to compute the two-point correlation function and saw that it was really that easy to find the BAO peak. It just sort of pops right out. Okay, so how are we doing on? Can I get a, let's see, can I get a show of hands if the download with the new link with this CloudFront URL is working for people? Okay, good. That's a lot of hands, but it was sort of 50%. So how about the other way? Is it not working for anybody? Okay, maybe people are just getting started. Okay. My notebook is caught up now. Everything's finished running, except for core func. So hopefully everybody else isn't far behind. If you're having catastrophic problems running the notebook, raise your hand in case there's a lot of people having the same problem. Okay, good. So today, the first thing we'll be doing is implementing an HOD function that tells us how many galaxies a given halo is going to have as a function of its mass. And we're going to do this in we're going to split the galaxies into two populations, centrals and satellites. We're going to start with centrals, which are going to be galaxies we will place at the center of mass of the halo. The mean occupation number is what the HOD gives us, and this just means the average number of galaxies that a halo of a given mass will have. And we're using sort of the original standard HOD for luminous red galaxies from this paper, and it has this particular functional form. So what we're going to start by doing is just implementing this function, turning this math into code, and then immediately after that, plotting the number of centrals versus mass to see what we actually just implemented. Okay, so this is we're starting with a pretty straightforward task, which is to fill out this function n_sen, number of centrals, which is a function of mass, and then two HOD parameters, log m min and sigma log m, which correspond to log 10 m min in the equation here and in the numerator, and then in the denominator sigma log m. So as the name suggests, these are sort of set the minimum mass scale and the scatter and the relation between number of centrals and mass. And we'll see how that actually affects the function when we plot it. Okay, can I get some raised hands if people's notebooks have finished running and are now caught up to this point? Okay, great. Yeah, I think we're ready to get started. We'll do the same thing as yesterday. I'll give you all a couple minutes to try to implement this yourselves, and I'll walk around. Raise your hand if you need help. And then I'll come back in a couple minutes and show you my solution. All right. Okay, I think people are moving pretty quickly through this section, and I have, yes, question. Oh yeah, probably something like 12 to 15. Yeah, yeah. So when you're plotting the function that you just wrote, you should probably you're plotting versus m, and m should be probably from 10 to the 12 to 10 to the 15. I'm gonna pull up my solutions again, because I'm sure I'm going to mess up something in implementing this function if I have to do it in front of everybody. Okay, so this is what my solution looks like. We're using the only, let's see, the tricky parts here are the fact that NumPy doesn't have an error function in it, so I use scipy.special.erf. And the other tricky thing is the fact that we're accepting the mass in just plain units, but then this other parameter is in log 10 units. It just makes the parameter more interpretable. So you have to remember to take log 10 of the mass in your function. Okay, otherwise, pretty straightforward, and we can plot it like this. Just plotting. Let's call this mplot equals numpy dot. Well, we're plotting versus log mass, so I think we should probably do log space from, let's try 12 to 15 and 100 samples. And we'll plot mplot versus n sen mplot, comma, okay, first parameter is log m min, and I wrote here we should do 13.5. It's a typical value for an HOD. Sigma log m 0.2, and if I didn't mess anything up, which I did, and since not defined, I forgot to run this cell. Okay, and I was a little bit off on the plotting range. Oops, no, I wasn't. I forgot to make it a log scale. So now I'm going to change the X scale to log. Okay, that looks pretty good. And we got to label our axes as always. The X axis is mass in units of m sin over h. And the Y axis is expectation value, which I'll do this way, of centrals, dimensionless. Okay. So the function we just implemented, question, yes.
Yeah, but the function takes m, like not log m, but now you're feeding m to n sen. Isn't that a bit strange?
Yep. The function takes m because that's the value that's in our catalog. So when we pass that field from the catalog, we want it just to be able to accept it directly. And then it takes the
MPLT is just already the log, right?
No, it's not. It's See, it has
Oh,
values
okay,
10 to the
okay.
12 to 10 to the
Okay.
15. It's evenly spaced in log 10. That's what log space does. Okay, so we see that this function is just taking us smoothly from 0 to 1. Question.
Is it okay to have a map behind the smaller map?
Yeah, I think that will, I think, I forget what the behavior of the error function is there. I think it just becomes an invalid value. And so, but the idea is that you won't have any centrals below the minimum mass, I think, but yeah. Okay, but yeah, the main idea of this function is that halos are more likely to host a luminous red galaxy if they are more massive. And this functional form is asserting that once you get to something like 10 to the 14 solar masses in your halo, you are definitely going to host a central galaxy. And once you're below something like 10 to the 13, you are definitely not going to host a central galaxy. Sorry? Yeah, why is it flat? Why does it not keep going up?
Yeah.
It's just because you can only have one galaxy in the center of a halo. That's sort of in this particular HOD model, and this is motivated by observations that there are brightest cluster galaxies or galaxies that seem to live at centers of halos. There can be only one. If there were two, they would merge and become one. But you can have a lot of halos in the galaxies in the outskirts of a halo, and those are satellite galaxies which can go have a mean occupation of greater than 1, which we'll see momentarily. Okay. Now that we have this functional form, we're going to select halo centers to be part of our galaxy sample with the probability given by this mean occupation from 0 to 1. So our next task is to fill out this function, which is going to take our halo catalog and then the same two HOD parameters using the same values that I gave you before. It's also going to take a random number seed because you're going to have to be using random numbers here. And then it's going to output an array of output n gal comma 3 output shape. So we're outputting halo centers of which there will be a number determined by the mean occupation, and they're each in XYZ position. Okay, question?
Yeah. So you said that seeing that in OpenG we don't have any.
Yeah, that's right. Yeah, or yeah, there's probably sorry.
Why is that? How?
Just because small halos have probably don't have the mass to. So luminous red galaxies are some of the most massive galaxies. They are. Yes, exactly. If we were plotting emission line, if we're doing an HOD for emission line galaxies or some smaller, bluer star-forming galaxy, those would live in smaller halos and have support on smaller masses. But it's particularly because we're looking at the HOD of LRGs, it has this form. Okay, so our next task is filling out this function. We're selecting centers, if I can spell centers of halos from, and if you remember from yesterday, the centers were in the column called X underscore L2CM, the center of mass of the halo. If a particular halo has an mean occupation of 0.1, it should have a 10% chance of making it into your sample. If it has an occupation of 1, it should always be included in your sample. You're going to use NumPy's random library to do this. And so, okay, so is the task clear for each halo? You can use the nsen function to compute a mean occupation fraction and And we're going to treat that as a probability that the halo center is included in our galaxy catalog. Okay, I'm going to let you think about that for a couple of minutes, and then I'll come back and maybe give you some hints. Okay, I'm going to give you sort of first hint, which is that you're probably going to want to call the function that you just wrote. We'll call this sen frac equals n sen with the mass of the halo catalog that gets passed into this function. And just passing through log m min, whoops, log m min and sigma log m. Okay. And then this is going to be between 0 and 1. So I'm going to treat it like a probability. And then for each halo, you're going to, yeah, what I wrote here, you're going to select centers of halos from this column using some condition here, using this central fraction. And this is gonna involve numpy.random, or equivalently this RNG object, RNG.random. Okay. All right. Keep working. I'm gonna keep walking around for another minute. Okay, I'm going to show you my solution now. So the key idea here is that you've converted with this function, converted your array of masses into an array of probabilities, and you want to compare each of those probabilities to a uniform random number between 0 and 1. And if the uniform random number is less than the probability of being included in the catalog, then you include that as a central. If it's greater, then you reject it. So I think this is going to look like, we're going to index the centers and said if the random number, okay, so we need to generate uniform randoms, which is this is just called random. We need as many randoms as there are halos. And we said if it's less than the probability of being included in the catalog, then we want to include it. And I think that's it. Going to now run this and find out if that's actually it. Passing it the halo catalog, log m min, we said 13.5, 0.2, and we'll leave the seed as it is. And we'll call this sen pos, the positions of our centrals. Going to run this. Okay, it ran. Give us a warning. It's probably okay. Let's look at it. Okay, great. We have about 600,000 LRGs. I think that sounds right from memory. We can compute some stats like how many galaxies did we actually end up selecting compared to our halo catalog. We selected around 4%. Okay, that seems sane. It's not 0 and it's not 1. Okay, does that make sense? Mm-hmm. Oh yeah, sorry. Yes, you could write. So NumPy has old style and new style RNG, and this is the new style. This is what we're all supposed to be doing now. Yeah, that's it. And this is good because if I had not included this, then I would have gotten a different number of LRGs every time I ran the function. So that's why it's a good idea to pass a seed as an argument and reseed the random number generator. Okay. And let's do this part quickly, because this actually reuses code that we wrote yesterday. So this should be pretty quick, and then we'll go to break. So now we're going to plot the 2-point correlation function, not of halos, but of the galaxies that we just generated. I called these positions senpos here, and this has shape n sen, which was like 600,000, comma 3, similar to what we were working with yesterday. And I think we called the function to compute the 2-point correlation function, compute psi. We made it accept an array of positions, so we can just pass the positions. And then I told you right here to first check the large scale 2-point correlation function using the same binning we did yesterday. So you can look back further up in the notebook and see what that binning was, and then do it again with a different binning and a different scaling, and you'll actually see something interesting. Okay, so you're gonna be call and plot this function twice, once for large scales, and then again for small scales. Okay, and I'm just gonna give you a minute on this one. It's reusing code that we wrote yesterday, so hopefully it'll be quick. I'm gonna walk around. Okay, some people are having trouble with core func, and that's this annoying thing that we talked about yesterday. Oops, sorry, I gotta find the spot again. Where if your positions are not on the domain 0 to L, then you'll get an error. And if you check your central positions, you'll see that they're from -L/2 to L/2, meaning -1,000 to 1,000. So the way to deal with that is to, before you try to compute the correlation function, is do what we did yesterday and wrap the positions using this %= to do it in place. And then if you inspect your array after doing that, you should see that the values are no longer negative. Check the min and the max and all that, and it should look good. Yeah. One is idempotent, which is a fancy computer science term for saying you can apply it multiple times and you will get the same result. Whereas if you so that mod is idempotent, whereas if you're just shifting things by L/2, then every time you add L/2, then you're changing the output value, and it doesn't matter if you're only running it once. But if you accidentally are running it multiple times or whatever, so one is just slightly safer than the other. That's how I would put it. Yeah.
But if you just include it when you're calculating it.
Yeah. If you apply it on the fly, and so you're applying it once, that's fine. Yeah.
Thank you.
Okay, I'm gonna show people my solution so we can go to break. So we need to look at the binning that we did yesterday for the 2-point correlation function. So I'm just going to copy this. It was from 1 megaparsec to 120 megaparsecs. And we can just drop that right in the function call, because why not? I'm gonna call this sen CF large for large scale. Run this, hopefully, okay, it's doing something. And I'll plot this too. And we know that we need to plot on the x-axis the sen CF large, and we're going to be a little lazy and just plot the left edge of the bin. Send CF large, and the notebook is telling us it's called psi. Good. Okay, and we get this shape, which reminds us what we did yesterday is to set the Y scale to log. Okay, and we see our BAO bump again, this time in galaxies instead of halos. Not too surprising. Something more surprising is going to happen if we plot the small scale correlation function. And I wrote here, we should do that from 0.1 to 20 megaparsecs. So let's do that now. Copy paste, we're gonna call this small. Probably do jump space, log spacing because we're doing log scale. Looks good. Fingers crossed. Okay, looks good. And copy our plotting code. Change this to small. Of course, this should really be a function. If we were being more careful. Okay, now we're plotting the small scale correlation function. This is still megaparsecs over h on the x-axis and the 2-point correlation function on the y-axis. Psi of r. Okay, what does this mean? Now we're zoomed in to sort of the one halo scale, which I told you yesterday was typically, depending on halo mass, around 1 megaparsec. And we're seeing that the correlation function is sloping from large to small, like we saw on the large scales on the right, but then on the left, it's plunging down to 0. So what does this mean? So this is called halo exclusion, and it happens because we defined our centrals such that each halo can only have one central. And if you imagine what happens in n-body simulation, when two halos get close enough together, they will start to merge. And at some point, the halo finder in the simulation will call that one halo. And so it can only have one central. But this is not observed in real on-sky clustering. In real on-sky clustering, the correlation function continues up and up and up to 100 kiloparsecs, 10 kiloparsecs. It keeps going until you get to the length scale of an individual galaxy, at which point you have galaxy exclusion, because at some point in the real universe, two galaxies will merge together. And so you can't have two large galaxies that are separated by a single kiloparsec. You would observe that as one galaxy. But this is halo exclusion that we're seeing here, and we'll see how to fix this by generating satellites after the break. So we'll come back in 10 minutes at 5:06. Okay, yeah, I'll stick around. Okay, let's keep going. I'm gonna try to get us out of here close to on time. I'm just gonna spoiler, we're not gonna have time to do any of this stuff with Numba, but if anybody is interested. Yeah, this is my favorite part. This is basically why I wrote this notebook, so I'd be more than happy to talk about it. Okay, but this part is we're going to add satellites to our satellite galaxies to our HOD model, following a similar procedure to what we did with the centrals, except this time the positions of these satellites are going to come from particles that we've randomly selected from the halo. For starters, though, we just need to compute the mean occupation number of satellites in halos. This NSAT looks a lot like NSEN that we had in the previous section, except it takes 4 HOD parameters, one of which is just shared with the centrals. So that one's fixed. And then I probably gave you, I gave you values for all these here. Okay. This one should be pretty quick. As a matter of fact, I think I'm just going to sort of code it live here while you all are doing the same, rather than the walk around, and then I'll walk around in the next bit. Okay, because this function doesn't require anything special from SciPy. This is sort of just Python NumPy math. And looks like m minus kappa times log m min. And this is a log, so we're going to raise this to the 10th power, or other way around, divided by log m1. Also needs to be a power of 10. And then this whole thing is raised to an alpha. Okay, I think that's it. Looking for. Yes, it probably should be, or we'll get an error, but I think I'm just gonna plot it and hope for the best. And I forget, yeah, I can probably look at my solutions also. Let's see what I did here. Yes, it looks like, yeah, okay. Yeah, and okay, good. Let's cut it off. So let's call this result. And then for result values that are less than 0, we'll set them to 0. And this will save us from having negative or whatever probabilities. Okay. Turn res. Let's plot this. For simplicity, I am going to go up here to where we plotted the HOD of centrals. This is now going to be nsat. I'm going to use some different args here. Log m min 13, 2, 14, 1. And actually, we're probably going to want to plot both on the same plot. So let me copy this guy. And like good matplotlib programmers, will label this equals sen, label equals sat. We're calling the right functions, nsen, nsat. This is now not nsen, this is n, and add a legend and fingers crossed. Nope, I forgot to run this cell. Okay, that looks, the scales are way off here, so I'm going to set a ylim. What does this look like? This is 4. So I will do. Okay, should probably be lower. Okay, that looks pretty reasonable. Okay, so this is saying that satellites turn on later than centrals. Meaning you have to have a big enough halo that it has enough mass to support a central galaxy and a bunch of satellites orbiting it. So this would happen typically for a cluster scale halo, 10 to the 14 or bigger. This is also saying that we can have more than one satellite, unlike the centrals where we can only have one per halo. Okay, this next part is going to be sort of the final tricky part of our HOD code, we're now going to generate satellite positions by placing them on halo particles. Where are the halo particle positions? They're in this array called, in the catalog called subsamples. And we're going to select the position field. So I'm just gonna put this here. Okay, there's like 70 million of them. They're in a very particular order though. They're ordered by halo. So the first halo has a number of satellite particles in this array given by this MP out A, number of particles out in subsample A. So if I print this, this is saying that the first halo has 0 particles. It won't get a satellite. Let's try a different one. 1,000. So this halo has 7 subsample particles. And we're going to select some number of these by a probability that's given by the mean occupation fraction. This is definitely the sort of, this is probably the trickiest part of the day. Yeah.
Are we just selecting particles from the probability we have, or will you guarantee that for each halo we see that exactly the number?
So you don't need to, right? So okay, so the idea is that for each halo, you compute a mean number of satellites, and then divide that probability across the satellite particles. So each satellite particle will have some small probability of making it into the sample. Now I wrote here, for each halo, which kind of suggests, oh, I want to do a Python loop over halos. That's not what you want to do here. This is sort of the key insight here. You're trying to, and I think I wrote that here. Oops. Try to avoid writing a Python loop over halos to accomplish this. NumPy can let you do this in about 2 to 4 lines. You need to think about the shape of the halo array and the shape of the subsamples array. And I'm going to let you all mull this over for a minute, and then I'll give you a hint. Okay, I will leave this notebook here and walk around. One little tip to get you started that I neglected to mention is that I wrote this parameter here called randoms. This should just be a set of uniform random numbers. It's important for the numba part, but we're probably not going to see that today. But that means that you should be doing something like this, sort of like we did before, just to pass an array of uniform random numbers. And then you're going to do something with them to and combine that with the number of satellites per halo and your halo catalog, which actually isn't an explicit parameter here, but you're certainly going to need it. It's probably, it's a global variable, but it's probably cleaner to pass it as a parameter. Okay, so this is going to be, okay. I'll keep walking around. Okay, a little hint to help you. This nsat per halo parameter is literally just the output of the function that we just wrote. And I think we call that nsat maybe. Yes. And it takes all these parameters, which I'm not going to bother to write out again. I'm instead going to copy it from here. Okay. Good. Does that make sense? This is the mean number of satellites per halo, ranging from 0 to infinity. All right, gonna keep walking around. Okay, I really don't want to go run overtime any more than necessary, so I'm going to give you another hint, which is that the key function is numpy.repeat. This is what's going to help you map halo probabilities to satellite particle probabilities. And I'm going to let you think about this for a couple minutes more. You're probably not going to have time to figure it out entirely, but I also don't want to keep people here late since we're already over time. So just a couple more minutes. Okay, I just wrote your last hint up here, which is how to think about these probabilities. If a halo has a satellite expectation of 5, so NSAT per halo for a given halo is 5, and it has 50 subsample particles, then you should give each subsample particle a 10% chance of making it into the sample, meaning a 10% chance of becoming a satellite. And you're going to use the function numpy.repeat to accomplish that. Okay, we're gonna wrap up here. I'm going to try to code my answer in front of you. I'm probably gonna mess something up because this is a tricky part and have to look at the solution. Okay, but we are returning satellite positions, and we know we're going to want to index the subsamples, their positions, and we are going to spread out the probability of n sat per halo over the number of particles per halo. And we need to repeat that probability for as many particles as there are in a halo. And then if this probability is less than the uniform, no, if the which side of the equation does the RNG.random go? Is this right? Somebody, other way around? Okay, good. Okay, so if this side of the equation is 0, then we, wow, my brain is completely fried. If this side is, if this side has a 10% chance of being selected, then we only want it to be true when this is between 0 and 0.1. So that seems correct to me. Okay, and then how many particles are there? It's len cat.subsamples. Okay. I do not know if this, it's actually cat. Yeah, it is cat in this case. Oh, thank you. Great. I do not know if this is correct. We'll find out in a moment. Shapes do not match. What did I do wrong?
So, I have a question.
Mhm.
In your last line, when you're passing values to GenSat.
Yeah.
And your second command you're using mplot.
Oh, yeah.
Should that be?
Yes, thank you. That's exactly what caused the error. Yeah. This is HM. Yeah, thank you. Okay, this should only take a second, and it ran. Okay, we got some satellites. We got about 95,000 of them. I think this is it. So okay, so what does this repeat function do? It takes a value and repeats it it takes an array of values and repeats each element in the array a number of times given by the corresponding value in a second array. So for each halo, we're looking at its expectation number of satellites, dividing that expectation over the number of satellites, and then repeating that probability for as many times as there are satellites. And those are just probabilities that we compare to a uniform random number and select particles based on that. Okay, and then all that's left is to measure the small scale clustering and plot it, which will borrow this plotting function and set 2PCF equals compute psi of sat pos. And then I think this can probably be same geom space 0.1 to 20, 100 samples. Plot this. Nope. Name error, set pause. Oh, I call it send set. Oh my gosh, I'm sorry. This is sat pause. Send set makes no sense. Set pause, and we'll wrap this to the box before we crash CoreFunc. Okay, this is our small scale correlation function. So we're looking at the sort of 1 megaparsec and the 1 to 2 halo transition here. And as expected, the clustering strength is really strong on a 1 halo basis. So we have all these little islands with bunches of satellites clumped together. And then out on large scales, we're basically just seeing the same large scale structure as the centrals. And that's pretty much it for LRG HOD modeling. If we were to, then we would probably hook this up to an MC chain, compute the total correlation function of the combined centrals and satellite sample. And then we would compute a covariance matrix from MOX and run an MCMC chain over the 5 HOD parameters that were fixed. In our example, they were fixed to values like 13.5 to 14, et cetera. But we would vary them and do inference over these parameters so we could constrain them or marginalize them out and infer cosmology. And this is the central idea of HOD. Everything else is just sort of decorations. You can add lots of ingredients, lots of additional flexibility, assembly bias, et cetera. And then you can also make it fast with Numba. You can write Python code that gets compiled when you run it. I'm not going to try to talk through it here, but I am going to share the notebook and the solutions with you. They'll be linked from the program website. And we're 20 minutes over, so I'm definitely going to stop here. Thank you all for your attention. I'll stick around if anybody has questions, but feel free to leave.